Okay, this was literally the best way for me to record of all the setups because I tried it on Windows and everything, and somehow none of them like my microphone. So we make do with what we have. Okay, so hi, this is CS2040S Recitation Video 1. I make it sound like there's gonna be more than one video. Um, but no, as you all know, this is replacement for Chinese New Year. Okay, so let's begin. So we're gonna cover a few things for this video. We're gonna do a review on algorithm analysis. It's gonna let me show you a little bit of we're gonna go through mostly basic stuff, but we're gonna do a bit of guessing and checking as well. And then we're gonna go through some stuff about algorithm design basics. So what I mean by this is that as a sneak peek, we're gonna talk about turning problem descriptions into algorithmic tasks. We're gonna try to look at different ways for us to measure the goodness of an algorithm. And also, we're going to talk about what it means to evaluate weak points of an algorithm and improve on it. So, I know hopefully you guys have looked at the recitation sheet and you know what I'm talking about, right? We're going to be talking about sharing our salaries for whatever reason and trying to compute a value from it, right? The average, in fact, right? The whole takeaway, I'm going to say this right now up front, the whole takeaway is not for you to learn that algorithm. That's not the point. The point is to sort of show you at a high level what it means to do algorithms. Because when you move on and you start learning how to make data structures and algorithms for different parts, right? This is the general framework. This is the general idea where we sort of say there's a scenario, there is some real life constraint, some real life requirement that we want, right? It's going to be stated in English, it's not in math, right? We sort of have to create a problem requirement out of it. After we do that, we try to come up with algorithms that fit that bill. And then we're going to see, okay, now that we have something that fits that bill, what are some points of consideration, right? Is this algorithm good in some regards and not others? That sort of thing, right? So it's not really meant to be like a formal like content specific thing. It's sort of just to get you through the problem solving process, right? From what I've been told, the O1S recitation kind of works the same way. It's mostly about problem solving. Same thing here. We want to keep that up. Okay, so let's get into it. How this video works is that it's not going to be as if this was the recitation itself, right? So typically for a recitation, what's going to happen is that there'll be discussions. You come to our recitations, we tell you to discuss with your friends, and then you start proposing solutions and stuff like that. And at times, what I will want you to do for this video is that we will want you to pause and think about some of the hints that we're giving, right? Before we present the solutions and stuff like that. I can't make it interactive. I can't say propose to me a solution and we think about it. We can't do that because I can't talk. You can't talk to the screen, right? So, we make do with what we have. Okay, so problem one. Let's go through the order of growth review, right? And we're going to use primality testing as an example here. So here I have a snippet of Java code, and right now it's basically saying that when n is small, we're just going to do some O1 work, right? Otherwise, we're going to go through n iterations, right? And we're going to call is divisible. So what's the runtime here? Well, it depends on what is divisible, right? Um, so what I mean by this is let's say that is divisible runs in O1 time. So if we know that to be true, what should the running time of is prime be, right? Well, we do ON comparisons, we do ON additions to our I, and we call is divisible ON times, right? And we know that basically because each time we call it, it's in O1 time. Hopefully you remember this from week 1, lecture 1. We talked about how this was ON times O1, right? So that's the answer here. Okay. Well, what about if is divisible wasn't on one time, right? What if we had a really expensive function to evaluate divisibility, right? So what if it was in one time? What is the running time now, right? If you haven't solved it, please pause the video, think about it a little bit. But if not, I'm going to reveal the solution here, right? It's basically on times on because it's on iterations. And each time it costs on time. Because of that, the worst case running time is on squared. Yeah. Um, okay. So one other thing that I want you to think about right now, incidentally, is that when does the worst case actually happen? Because I want you to notice that when is divisible is true, we actually return false, and that might happen early, right? So when is the exact worst case for like this question, right? When do we return stuff like that, right? So I I think one thing we need to think about, if you haven't noticed, right, is that I've been telling you a very loose bound, right? So I've been saying ON because it's ON iterations, and then I tell you, hey, actually, there's ON iterations here, and and this costs O(n) times, so we're gonna say O(n) times O(n) is O(n) squared, right? But at this point, I think it's a good time for me to also pause and say, this is how we usually do things. And in fact, like I mentioned before, in week 1, this is a general rule. This is how you would apply it, right? But I kind of want you to think a little bit about what this is doing, right? Like what the actual running time is. Is it possible, for example, for the for loop from I equals to 2 to run all the way to n, right? When does that happen, right? Pause and think a little bit about when that happens. Like, is it true that will we might early return sometimes, right? So for example, for the value 8, the moment we test 2, we know that it's true and we will return, right? But are there values where it's n and we actually go through all values 2 to n minus 1? What kind of values are those? Think about that for a little bit, right? While we move on with the analysis. Okay, so for example, something slightly more involved would be OI time, right? So assuming that we really do hit all n iterations, right? What is the running time for is prime, right? So now I can't just say a loose bound. It is true that a loose bound is ON times ON. This is true, right? There's nothing wrong with this, right? But we have to be very careful if we want to be a bit more precise and tight with our bound, right? So in particular, it's more accurate to probably say that the amount of time it takes on the inside is actually 2 plus 3 plus 4 until n minus 1, right? And if you sum this up, it's still, yes, you arrive at the same conclusion. It is ON squared, but we're being very careful with making sure that we aren't throwing away like like we aren't just being too loose with our bounds and stuff, right? Okay, so I want you to come back to the question that I gave you just now about how, like, when do we really hit n, or like when do we hit really close to n, right? I'd argue that if n is a prime, we go through all the possible iterations, right? We go through from 2 all the way to n, right? What about if our value n was composite? In other words, it's not prime. Can we argue that where n is not prime, it kind of stops earlier, right? In other words, even if we wrote the for loop like this, we almost will always early return. And where and how early do we return, right? So maybe something to think about. I'll give you a hint. You proved this fact in 1231S last semester in your tutorial. How do I know? I taught the tutorials last semester, right? So for those of you who don't remember, right, a value n has, if it can be written as a times b, right, is such that either a is less than or equals to square root n, or b is less than or equals to or b is equals to less than or equals to square root n, right? Now, if you're prime, the only possible value that's less than or equals to square root n is 1, right? And that's why we're skipping it here, right? That's why we're starting from I equals to 2, right? Which means that if you are prime, there is literally no other value up to square root n for which it divides n. And if you're composite, you're guaranteed, actually, surprisingly, that there is one more value that is less than or equals to square root n. Because of that, well, that's how it works, right? Which means that we could actually come up with a new algorithm that stops at square root n, right? In fact, this should be less than or equals to, because, for example, a number like 9, we want to stop testing at 3, right? We don't want to stop testing at 2. So that should have been less than or equals to, okay? But let's say for now that this was our new function, right? And we know that divisible testing ran in ON time. But what's the runtime now, right? Now we run square root n iterations. This is guaranteed. Even if you're prime or not, it is square root n iterations, okay? And the time it takes for you to run this is ON. So n times square root n, last I checked, is n to the 1.5, right? So this is how you should solve it. For example, hopefully you've thought of like all of these before. So one more interesting one would be I equals to 2 to less than or equals to square root n, right? And let's say for now it runs in OI time. So what's the bound, right? Well, then you kind of have to do the same thing as before. You don't say 2, it's 2 plus 3 plus 4 plus 5 all the way to square root n. And again, same trick as before. This is square root times square root. It's roughly square root times square root plus 1 over 2, which is basically ON. Yeah? Okay. So that's kind of the idea. Now the interesting one, 1C, right? So I talked about guess and check, and we're gonna basically see in action. So let's say that our is divisible right in O1 time. What's the running time of is prime now? we're making a recursive call. So I don't know if you guys remember this, but basically I mentioned this before. We want to bound a recurrence. The first thing to do is to write the recurrence, right? So we want to say that Tn is the running time for our function. It basically makes calls to recursive calls, right? From 2 to square root n. Oh, look, the equal is here now, right? So we basically want to say from I equals to 2 to square root n. This should be what we write. And because we're also doing square root n many checks here, we're doing square root n many increments here, we're doing square root n many function calls here, we're doing square root n tests here, we need to write square root n here as well, right? So this is the total time it takes to solve all your recursive calls. This is the total time it takes for your current level, right? So now I have the recurrence. The question is, how do we bound it, right? So how do we bound this? Okay. So you're about to see how I do guess and check, by the way. I'm about to show you the trade secret, right? The guy who does like all these bounding tricks like all day for his job, right? Like what does he do? Right? I'm gonna show you what a pro does. So well, I was kidding, by the way. I hope you guys don't hold my feet to the fire. It's not like I'm actually really good at this, but I would argue that I know enough to share something. Yeah. Um okay, here's how I would start. In fact, it's not just how I would start, it's actually how I did start, right? My first observation was the following. Tn has to be at least square root n. This is literally because of how we wrote this, right? The function literally has to take this much time at minimum. Forget the recursive calls, it has to take this much time minimum, right? I think that makes sense. Okay, well, let's move on from there and say that because this is our observation, right, that Tn is at least square root n, I think it stands to reason that we should try to guess whether Tn is square root n, right? After all, it's at least square root n. Maybe this is the first starting point on our guess, right? If I'm being honest with you, I looking at this, I myself did not know what the solution was, right? So from this observation, the first question that I would ask myself is, how about we just try this? And in fact, I wasn't sure whether it was the answer or not, so I just tried it, right? So how do we do that? Well, guess and check is the best method, right? We have a guess, we might as well check it, right? So I'm going to assume that Ti is d times Ti for some constant d, and for all I less than n. This is our inductive hypothesis. Okay, so I write down my first line, which is by definition, right? And then I'm going to replace the Ti by d times square root I. This is by my assumption, right? Notice here that my I ranges from 2 to square root n. So that happens, it's good reason this is it stands for good reason this is less than n. So we can do the replacement. This is by our inductive hypothesis. Okay, what do we do next? Well, here's a neat trick that I learned from CLRS that maybe you guys will learn from now on. But the sum, since it was from 2 to square root n, I'm just gonna drop the early terms of my summation. So instead of starting my sum from I equals to 2, I'm gonna start my sum from square root of n over 2. Yeah. Okay. And for the sake of convenience, I'm gonna say that like well, let's say these like greater than or equals to 1. So let's just drop that as well. It makes my analysis a lot easier. Right. Okay. So I dropped off the first half of this summation. So I'm starting my sum from square root n over 2. Okay, I copy pasted this over. What do we do next, right? And by the way, if you're wondering, Eldon, why are you doing greater than or equals to? I thought we were trying to bound it. So why are we doing this? I don't want to show it's at most square root n. Well, yes, but the first thing that I wanted to do was a sanity check, right? Our goal was to show that Tn is O of square root n, right? Or maybe theta, let's say, right? So if this were true, right? If this were true, we should be able to prove that this is at most like something times square root of n. Make sense? Okay. So what happens if the function that we get here happens to be much larger than it? Like let's say it's like n to the 0.75. If from whatever math we derive, we find out that Tn is something big and not square root of something much larger than square root of n, we know that our guess was wrong, which is what I'm going to do, right? This is exactly what I did. I said, okay, I'm going to guess the square root n. I'm going to see if I can prove that it's wrong, funnily enough, right? So let's see how far we get, right? We know it's at least the sum. So what am I going to do now? Well, I'm trying to lower bound the value. So I'm going to take I and set it to be the lowest possible value in this summation, which happens to be square root of n over 2 itself, right? So square root of n over 2 is n to the 1 over 4 divided by square root of 2, right? Okay, and plus cn, we still keep that over. Okay, well, if that's what the math says, then don't forget, because we're summing this n to the 1 over 4, how many times? Around square root of n times. So square root of n multiplied by n to the 1 over 4 is basically n to the 0.75. So what have we shown? We've shown that assuming that ti is, we wanted to show that tn is square root of n. Yeah. So we made this hypothesis and we tried to confirm that Tn is square root of n, but somehow we arrived at the conclusion that Tn is really big. It's like n to the 0.75, which last I checked is much bigger than square root of n, right? So this is an issue. In fact, what it tells us is that our assumption is wrong. Okay. In other words, our guess was too small, right? Our guess for Tn was too small. But we've at least done some math, so we should use it, right? We should make use of this fact somehow. So instead of n over like square root of n, let's try something like n to the t. Okay. Now this is also not a very standard trick. This is something that I do, right? So this is let's put it this way. I suspect that Tn, right, is going to be some polynomial. Let's say let's say n to the t, like O of n to the t, I guess, but I'm just like scribbling here. So we want a guess where we can put this as t, and what's going to happen is that we want it so that we can get the math that like we want to be able to confirm if it's it, we want to be able to confirm this n to the t, right? So let's try doing it. Okay. So instead of square root n, I'm gonna guess n to the t. So I'm gonna update my inductive hypothesis to say d times I to the t. Okay. So let's look at what happens. We write our Tn using the definition of the recurrence. Okay. We use our inductive hypothesis again. Nothing special here. This is the same. D times I to the t, same as before. Okay. Now we're going to basically again lop off the first half of the summation. Yeah. No new tricks here. Well, not yet at least. Okay. So throw away the first half of the summation. Okay, what happens next? Okay, well, what's the smallest value of I now? Well, it's still square root of n over 2. So we might as well write that, right? Square root of n over 2 to the power of t. So square root of n over 2 to the power of t, right? This should have been 2 to the t, right? I guess. Yeah. Okay. Well, I argue this is around this value, n to the t over 2, right? T here is constant, right? T here is constant. Okay, so this should be like theta of n to the t over 2 plus 0.5. Sorry, the 0.5 here is because this summation runs a square root of n times, so it's multiplied by square root of n. So this is t over 2 plus 0.5, right? So remember, we wanted a guess for Tn, right? So what we actually want is that Nt is at least n to the t over 2 plus 0.5. So in other words, we want that t is at least t over 2 plus 0.5, which means that t has to be at least, t over 2 has to be at least 0.5, which means that t is at least 1, right? And if you think about it, the fact that we want this, therefore we want this, kind of tells us why our initial guess was bad, right? When t was 0.5, right, it didn't meet this requirement. So the proof failed, right? So let's fix that. Let's set t to 1, see what happens, right? So we have a new guess, third guess, right? I'm going to guess that it's linear. I'm going to guess that Tn is On, right? So what do? I assume that Ti is equals to d times I for all I less than n. Then again, copy paste the definition of the recurrence, replace Ti by its inductive hypothesis. Oh, look, doesn't this look familiar? I'm summing I from 2 to square root of n, and I'm summing I itself, right? So if you remember, this is kind of basically square root of n times square root of n plus 1 divided by something like divided by 2, which is basically On, right? Theta n, in fact. So it's theta n. So now my guess follows through. I'm not being very rigorous here because like the whole point of the recitation is a sketch, right? Like if this was in person, you wanted more details, you'd press me and I'd show you how to do it properly. But for the sake of time, it's a 1 hour slot. We need to keep chugging along. Right. I promise me I could do it formally, but like to do it on slides and to do it like in person would take a bit of time for me to explain in detail. But this is the idea, right? I encourage you to try to do it formally, and you can check your solutions with me if you want on the forums, right? Okay, so moving on, let's talk about problem 2. Okay, so Let's talk about how much money people make for whatever reason. Um, so the problem setup is like this. I hope you read the question sheet, but it's basically saying, let's say that we want to find the average salary, right? How do we do that without revealing our own salary in the process, right? So for example, I have values 50, 20, 20, 25, and 10 here, and we want to compute the average, which happens to be 25, by the way, right? If you can check if you want, just sum up all the values, divide by 5. It should be 125 divided by 5, which is 25. Yeah. Uh, and we kind of want to do it in a way where we can sort of like collect our like the average value, but we don't know what everyone else's value is. So let's say we're this like teal, like dark teal, dark blue person on the top, right? We know our own salary, and that's fine. We know what we know is ours, right? But we don't know everyone else's salary. And this applies to everyone, by the way. So for example, like the yellow lady on the left, like she should know her salary, but not anyone else's, right? And it kind of makes sense that we want to design a system like an algorithm where everyone has to communicate something. Ideally, not their salary. Ideally, they don't reveal it, but they should still say something and they should participate in the protocol. Make sense? Right? So it's not it. I mean, they should say something. They should offer some information. They should send some messages. But the question is more like, what should they say? Right? So coming up with an algorithm is probably telling them, well, you need to do this, right? You need to provide this information, and everyone follows these instructions, and we will all find the average without revealing our own salary, right? So here comes the interesting part. Let's take a bigger step back and ask ourselves, how do we define what it means to not reveal, right? So why do I mention this? I'm not trying to be like vaguely philosophical. It's because our definition determines what kind of algorithm we create, right? So depending on what we want, the design of our algorithm is different, right? And this is something that you'll actually see, especially in like, I think like if there's an intro to cryptography course, you'll see what I mean. There's like many definitions of privacy, and depending on the definition, a different algorithm comes out, right? So we're not going to be too formal because we're not an intro class to cryptography. So I'm going to use one of the following instead, right? Let's think of the following. Maybe one potential definition. Like, by the way, like you should have like tried to think about some of these as well. But if you've already reached this point in the video, you can try to think about what these mean, right? I think that's also very useful. So maybe something like, upon observing any messages sent, any number within a range, right? So this range here, let's say it's like 0 to like some insanely large number that no one is able to make, right? Like take Jeff Bezos's number and square it or something. Let's call that T, right? So upon observing any messages sent, any number within some insanely large range is equally likely to be the salary, right? Well, that might be interesting. We should probably try to do that, right? We That's one possible definition. Another possible definition might be plausible deniability, right? Where we say, oh, it's possible my salary is X. It's also possible my salary is not X, right? You might see how these two definitions are different, and I would love to discuss this if this was in person, right? But plausible deniability seems a little weak. It seems like we're not talking about how relatively certain we are that it's X versus not X. Maybe it's a coin flip, right? Maybe we're like 50-50 certain it's $20, and we're 50-50 certain it's not $20. Well, that means there's a good chance it's 20, right? Or maybe not, but I would bet my money on 20. Whereas with definition one, I would have no idea what to bet what your salary is, right? And at this point, maybe you're taking an even further step back, and you might be asking yourselves, why are we designing this algorithm in the first place? Like maybe everyone shouldn't be so shallow and just share their salary. Um, this is actually more of a brain teaser and more of a motivation to design private algorithms in a distributed system, right? Okay, many buzzwords, I know, but think of it in the following way. Let's say that you were working to collect government census data, right? So census data here is kind of like, for example, let's say you worked. One of the other examples that I know of that people always talk about. Sorry, I didn't make pictures for this, but one of the other examples that I know people talk about is, let's say you work in the U.S. and you want to take census data on how many people own guns illicitly, right? So if you send out a survey and you don't provide any privacy guarantee, no plausible deniability, no nothing, right? No one's going to answer your survey willingly. No one's going to answer your survey honestly, right? But you can imagine how maybe I say to myself, we want to build in a mechanism where there is some plausible deniability so that we can find out how many people have illicit and illegal guns, right? We want to take a poll, a census, so that we can make governmental decisions based on it, for example, Well, you could do something, for example, like say, okay, to provide you plausible deniability, our algorithm will collect your answer, be it yes or no, and with some probability, flip it to be a yes, right? It turns out even with funny data perturbations like that, you can still do statistics, by the way. You can do really good statistics on it, right? But the government can't knock on your door and say, hey, you own illicit guns, right? Because there's a chance that it was the algorithm that flipped your no into a yes, right? So they can't act on that, for example. That's one of the other examples as well, right? So the point is that like algorithms like this are useful and it's something to think about, right? Okay, so hopefully I've convinced you that this is worth studying, right? And for now, also like when designing the algorithm for our current problem, I'm gonna make an assumption. I'm gonna make a simplifying assumption that everyone is honest and cooperative, but is curious. Okay, so what I mean by this is that we're gonna design an algorithm that everyone has to follow. Okay, they're not gonna deviate from it, but they whatever information is presented to them, they may make use of it after that. Okay. So at this point, you might be thinking, hey, although this is not really solving the problem, why can't we just consider like an unrestricted case? Well, this is also part of problem solving. I want you to think of simplified versions of problems first sometimes, right? For now, let's see how far we get. Okay. And after we do this, we can iterate and see what kind of algorithms pop up, right? So slow, one step at a time, come up with an algorithm. Then we look at it and say, what are some weaknesses? Where is it slow? Where is it inefficient? Where is it good? Where is it bad? And then we try to fix it, right? Okay, so it's your turn. I'm gonna give you a hint, right? Can you let's say that I know I said they had to send messages. Let's say that we restricted the messages to be sent in a ring, right? Can you think of a way where we can sort of get everyone to communicate some values to each other so that at the end of the day we can compute the average? Pause the video, try to figure it out. Okay, I'm gonna assume we paused, right? I don't have to pause, but I'm gonna assume we paused. And let's think about it. Okay, so here's my proposed algorithm one. It might be good, it might be bad. Let's see, right? Everyone's gonna sample a random number between like let's just say R1, person one samples R1, person two samples R2, and so on, right? We're gonna add your sample value to your salary, and then we're gonna send it, right? So how do we send it? Well, person one just takes R1 plus 50, sends it along to person two. So person two gets R1 plus 50, R1 plus 50, right? And then after that, person two is basically going to send R2 plus 50 plus 20, right? In other words, take the value that they received, take the $20 plus the R2 that they sampled, right? Add it to the sum, right? And keep accumulating this, right? So this is kind of an invariant if you think about it, right? So person three just adds their R3 and their $10, so on and so forth, right? So think about what person two sees. Person two sees a random value plus 50. They don't see the two values separately. They see a random value like 55 or like 100, right? So on and so forth, right? So at the end of the day, what does person one get? Well, person one gets the total sum of all of the random values plus the total sum of the salaries, right? That's kind of an issue because we want the some of the salaries without the random values, right? So we need to remove it. We know person one has value R1, so we can remove it and we can cut it out. So now it's just R2 plus R3 plus R4 plus R5, right? And we can rinse and repeat this process, right? So what should person two send to person three? Think about that for a little bit, right? So pause the video if you have to, but I'm moving on. So what you should do is basically get person two to remove R2, right? So you get R3, R4, and R5. And you can imagine how person three removes R3, right? So R3 is gone from the next message, and R4 is gone from the next message, and so on and so forth, right? And then this person gets the entire sum. They can send it back to the first person if they want to. That's fine. But basically, someone has to distribute the final sum to everyone, right? So everyone receives their sums, adds it up, and then well, they already have it added up. Sorry, like they all see 125 basically, right? But the point is that they should all divide by 5, and they should get the average value, which is 25, right? Okay, so have we achieved our goals, right? So I argue that we've definitely computed the average. It makes sense, right? And I promise you that everyone's faithful. We didn't screw the protocol in any way, okay? But is it private, right? So intuitively speaking, if this was really all there was to it, it's true. It would be private, right? So let's start sort of like thinking about what it means to be honest but curious, right? So let's say that these two people were colluding, and at the end of the protocol, they went home and maybe they were married or something, and they discussed, right? They said like, hey, what values did you see? what values did I see, right? So based on following the protocol faithfully, can we think about ways that they could get some extra information? And I'll give you a hint. This person is going to be compromised somehow, right? So think about how they can achieve that. Pause the video and try to figure it out, right? So here's an idea. In round one, when person one sends R1 plus 50, right? We know what our person one knows what R150 is, right? And then like in the same round, basically what's going to happen is that this person is going to receive R1 plus R2 plus 50 plus 20, right? So you basically figure out in round one, R2 plus 20. This is a typo here, right? So because we know what R1 is, we know what 50, we know R1 plus 50, so we can just subtract this away, and we basically know that it's we know what this value is. If we don't know what R2 is, we need to find that out. So we can't figure that out in this round. But which round can we figure that out in? Well, the next one, right? Because in the next round, what's going to happen is that when this person removes the R2, we can basically find the difference of the two values, right? So we know what R2 is, we know what R2 plus 20 is, so we just do a simple subtraction and we figure out that they earn 20 bucks, right? That's the idea, okay? So that's a weakness. You know, we designed an algorithm, it computed the value, and it kind of made sense, but somehow in light of colluders, it's not the best thing that happened, right? Like it's not the best way to go about doing this, right? That was issue number one. Issue number two is that I would like to mention that we didn't really specify exactly how we should sample our random values, right? So I just said, okay, there's R1, R2, R3, R4, and R5, but we didn't really say like what distribution they should come from, right? So to sort of illustrate my point, right? Let's just say that we said, okay, sample our random values from some range like 0 through m, right? Think about what happens if we send something like m plus 50, right? How might this cause an issue? Pause the video, think about it a little bit before I show you an example, right? So, okay, I hope you pause, but here's the next point, right? So I'll give you an example, right? If we weren't very careful with our distribution, one thing might happen is that let's say we sample our values from 0 through 10, right? So what happens if we set something like 60, right? Then the person who looks at our message, the second person, could just look at it and say, oh, we now know that their salary can range from 50 to 60, right? Because it could be 50 and you sampled 10, right? Then I saw value 60. Or it could be the case that you sampled 0 and I saw value 60 because that's the value it is, right? So even though I don't know your exact value, this might be plausible deniability. I have a ballpark, right? This is very different from me saying that it's completely uniform and random from some very massive range, right? This is now uniform and random in a really small range that I'm not very happy with, right? You might think to yourself, oh, we can fix this. We just make this very big. Turns out that that's not really the case. You can think about why, right? So just to bring it back to the previous point, is this an issue? It depends, right? We do have some plausible deniability, but this doesn't look very uniform, right? So let's think about the flaws of our algorithms, of our algorithm, singular, right? So first of all, there was this collusion issue, right? How can we fix that, right? So think about this for a second. When are two colluders able to exploit information about someone, and when are they not, right? I'll give you a hint, something to do about placement, right? So if you pause the video if you want to think about it more, but basically the idea is that if they're sitting next to each other, they're kind of harmless, right? Because you're not sandwiching anyone, so you can't really exploit information about anyone specific, right? But maybe the point is that if we don't know who are the colluders and who are not, we can't say when exactly like that's going to happen, right? We can't just run the protocol and say, okay, I trust you, but I don't trust you, so the two of you sit together. We can't really do that. But one nice thing we can do is basically shuffle them, right? So here's fix one. Let's just shuffle the participants, right? This way, if there's a chance that there are two colluders, there's a chance they're now side by side, in which case they won't be able to sandwich anyone, right? So, okay, at this point, hopefully this gets some of you thinking, what if there are more colluders, right? Well, here's the general idea. I like to argue that if the fraction of colluders is small, then we're probably safe, right? and then there should be some decent probability that no sandwiching happens, right? So now that I've mentioned this, right, one really cool thing, well, we don't have time to do this in the recitation, and it's not by design that we do this, but one really cool thing that you might want to think about is this challenge, right? Now that I've mentioned this, oh, we're shuffling, right? So maybe try to analyze how good the shuffling is, right? So given n people and k colluders, right? Given that we permute them at random, what is the probability at least one colluder will be sandwiched by some colluders, right? Analyzing this and producing a probability will basically tell us what is the likelihood that this algorithm succeeds, right? In sort of preventing colluders, right? That would be an interesting thing to find out, and it's also part of how you analyze your algorithm, right? Okay, but moving on, let's talk about fix two. There's many things to talk about. It's supposed to be very open-ended. I could only cover so much, right? Um, but fix two is sort of like it's very interesting. It's a bit intricate, and the difference is subtle, but it actually fixes it, right? What we can try to do is pick a very large value, let's say 1 trillion. I let's say we're not working in Zimbabwe where we have like 1 trillion notes and stuff like that. Let's say like we're working in Singapore or something where no one really earns a trillion, right? Um, what we can do is sample a random number within this range. Now we're being precise, right? We add it to our salary and then we mod p. Okay. So you can try to prove that this works. It's very interesting. The intuition is that now it works because there's a potential for a wraparound. So assuming we don't know where everyone sits in like any rough region, any number is equally likely. Right. So if you don't have any prior information about which bracket they're in, then this kind of like shuffles them around pretty well. So now someone is equally likely to have earned $0 compared to like 500, compared to like any feasible number, right? It is true that maybe someone comes back and they report a value of like 9999 million or something, and then you'll be like, okay, you probably don't earn that much, but yeah, okay. Uh, so some caveats to note: there is still a small chance of a sandwich happening, right? So for example, with 5 people, it's pretty like I think it's pretty likely that someone's gonna get sandwiched. Uh, so there is a non-zero probability. What is the actual probability? I don't know, right? But maybe let's try to move beyond that, right? So at this point, maybe your boss is not very happy about this, and we want to just completely eliminate it. So we might need to break the mold of this solution that we're working with, and instead of just tweaking it, we might want to consider a new one completely, right? So a great starting point on how to do that would be to think of like the following, right? Let's think about what this algorithm needs, right? So for this algorithm to be correct, we need the sum to be preserved, right? So any randomness that we add into the sum has to be removed by the person who knows the randomness, right? So if I know R1, you have to pass it back to me to remove R1, okay? Maybe we shouldn't have this bottleneck thing, and we might want to think about other high-level operations that preserve a sum. I know this hint is very vague, right? But maybe think about it a little bit. Yeah, I'll give you a hint though. It has nothing to do with multiplication or addition or something like that. We want to think about something crazy that preserves summation. And I want you to specifically avoid this whole ring structure, right? I want you to stop passing messages like in a ring, right? So doing this is bad because sandwiches happen and we want to avoid that, right? So what can we do? Pause the video and think about it. Okay, moving on. So here's algorithm 2. Here's the idea. How about we take our salary? So let's take the first person as an example, and we break it up into 5 parts, right? If there's 5 people, let's break it up into 5 parts. Okay. And here's what we're gonna do. We're gonna send 4 of these parts to other people. So for example, person 1 gets $1. Well, they don't get the actual money. They get the quantity, right? They get 1. Person 2 gets 29. Person 3 gets 10. Person 4 gets 3. You keep the 7 for yourself. This is private. Yeah. Um, okay, so likewise, person 2 might have an earning of a salary of $20. And what we'll do is that we could even split them to negative values, right? And uh take note, this all sums up to their original salary. Now, at this point, it's very interesting. You might want to ask yourself, why do we send negative values, right? Think about how if we only insist on sending positive values, how that might leak some information about our salary and how this might fix it. Yeah. Um, okay. Well, what do we do after that? So let's look at person 1 again. Person 1 kept their own private share, and everyone else sends like some share to them, right? Like they broke up their salary into a few parts. So let's say X2 is person two's share of their salary, and X3 is from person 3 share of their salary, so on and so forth, right? I argue what person 1 should do is take all of these values, sum them up. Let's call it S1, right? So everyone makes a piece this way. S1, S2, S3, S4, and S5, right? So everyone kind of gets a broken piece and they all add it together. What should we do with this? Pause the video, think about it, right? Okay, so what I argue they should do is that they should take all the S values and they should just, again, send them to each other, share it, right? And then everyone can collectively compute this value, right? So what's going to happen now is that this, again, is the sum of everyone's salaries, right? Now that aside, right, you basically you basically can compute the average this way, right? So again, like, because the 50 is broken up into multiple pieces and sum back to 50, you're sort of just shuffling it around. Okay. Okay, so it probably it definitely computes the correct value. The question is whether it solves the collusion problem, right? So here's the intuition. If someone doesn't see all the parts, they probably can't figure out what someone has, right? So in other words, if I have two people who are sandwiching anyone, it doesn't really matter because they don't see the remaining other parts, right? This is invisible to them. They can't tell what salary you have. That's the idea, right? Um, okay, but does it completely eliminate the collusion problem, right? So we said sandwiching is not possible anymore. But what about other collusions, right? Like, is it at all possible? What if we have more colluders, right? So I argue that if everyone else is colluding, like this is like when the whole world is out to get you, for example, right? Then you're still in a pickle, right? Because you've sent your share to everyone, and I know you've kept the piece private for yourself, and you might think, okay, if I have like my own value here, they can't figure it out, right? I argue that in the n-1 case, it's basically impossible, right, to some degree, because if all n-1 people are colluding, it actually doesn't matter what algorithm we propose. Once everyone, when I say everyone here, I mean like all the colluders, once they all know what the average is, right? Everyone knows the n-1 salaries that they have, right? So taking the n-1 salaries as well as the average value, they can figure out what salaries you have. So at that point, it's kind of moot, right? Okay. And it's very important to note here the average is the exact average, right? This is the exact value. Okay. So let's compare the two algorithms. Like we've done a lot of design. Let's compare the two algorithms, right? Besides the stuff that we mentioned about collusions, right? So that's what we focused on. Let's think about performance, right? We haven't talked about that in quite a while, and maybe we should, right? I'd argue that for the round robin algorithm, the one where we send things in a circle, right? The latency of this algorithm is high, right? Because the final answer of this algorithm depends on the two end messages being sent, right? So there's two end messages that are being sent, but the problem is that the ith message depends on the I-1th message, right? The third message depends on the second message. 10th message depends on the ninth message, stuff like that, right? So the more people we have, the longer it takes the algorithm to finish, right? Because we count the amount of time as the time taken since the protocol started, right? We need to send it to the second person. The second person has to do a bit of computation. The third person has to wait on the second person, right? Before he can do his part, stuff like that, right? So I'm just gonna call that latency. It's not a very well coined term, but you can imagine how, if we're being a bit philosophical here, it kind of represents what we want to represent. That is to say, we expect that the more people there are in the system, the longer it's going to take for us to figure out this thing, right? Okay, so now that I've mentioned these two things, this latency thing and the number of messages being sent, can you try to apply the same analysis here for the other algorithm, right? Pause the video here and try to work out asymptotically at the very least, right? What the quote unquote latency should be and what the number of messages should be, right? Now that I've brought up these two aspects, try to analyze the second algorithm in this way. Pause the video, figure it out. Okay, so I would argue that the latency of this algorithm is lower. Why? Because each person can compute their splits and sums at the same time in parallel, right? So everyone can compute the splits first, right? That all at the same time. They all send their values to each other, right? They all receive the values at the same time, and then they all sum up the values, and then they send it again to everyone, right? So in terms of rounds of communication, there's only two rounds, right? Like one round where everyone just massively sends messages to each other, and then another round again where everyone massively sends messages to each other, right? But the trade-off here is that the total messages sent is theta n squared, right? So if you don't remember why, think about it this way. This is a complete graph, right? A graph with n nodes has n squared edges, right? So it stands to reason that the total messages sent is basically n squared, right? Okay, so I made a table here. Sorry, slight typo. This should have been on theta n, right? Okay. So I made a little table here that kind of like tells you roughly uh like what to expect, right? So there are a few aspects of this algorithm that we might want to look at. How well does it tolerate colluders? We know that the round robin one depends on the fraction if we're trying to shuffle, but it's particularly vulnerable to the sandwich attack, right? The broadcast one is kind of fine. It kind of works really well. You up to n-2 colluders. It's kind of great, right? Um, okay. What else? So the latency for the round robin is not great, but the number of messages sent is kind of what you expect it to be. This is optimal, by the way. Like, you think about whether you can do fewer than ON messages. I think that would be difficult. Um, right? But at the same time, the broadcast one, even though it seems to work really fast because it's really low in terms of latency, the amount of messages sent in the entire network is really high, right? And maybe that's something you might be worried about. So you see how if you have like these many columns, it's sort of complicate. Well, I would say complicate, but it's more like it makes it very interesting that there is no such thing as one best algorithm, right? Um, yeah. Sometimes, let's say you're worried about network congestion. Oh, I guess that means you might want to opt for round robin, and you might want to pay the cost of being a little more susceptible to colluders, right? Or maybe you have like a really good network and you aren't that worried about it, but you want to compute these things as fast as possible. Well, like then maybe you want something a bit lower in terms of latency. In which case, you should go for this, right? You see what I mean? It's like sometimes it's very hard to decide what the best algorithm is, and you need to build a table. Um, I don't know if you know how engineers do things, but I don't have a chart off the back of my head, and I didn't find time to put one in the PowerPoint. But if you look at YouTube videos, for example, by Real Engineering, right, and you talk about how they design fighter jets or how they design the SR-71 Blackbird, right? They have like all these beautiful charts talking about how there's like these trade-offs on these like curves that says like, okay, so if you want to travel at this speed, this is the amount of fuel that you're going to burn. So we should be using like this engine. Like we want to use this engine because that's like maximum fuel efficiency, but it doesn't work. It doesn't perform very well, like for maintenance, like or sometimes it leaks fuel or it has like high maintenance costs or like it doesn't excel at other aspects like maneuverability and stuff like that. They have like many charts, many tables to sort of do trade-offs. And this is our version of engineering where we have like 5,000 algorithms and we need to sort of figure out what's good and what's bad. This is what it looks like. Yeah. So in that spirit, right? Let's just do a little bit more. Okay. So let's say that we want to beat our n-1 colluders scenario here. Okay. And I already mentioned that with n-1 colluders, if we computed the exact average value, this is nigh on impossible. Everyone's gonna figure out what your salary is, right? So at this point, we might want to shift not our algorithm first, but our goalpost, right? So what if we weren't so strict about privacy? So thus far, the solutions that I've shown you, you can tweak them to work for this whole uniformly random definition, right? Which was definition one that I showed you. But what if we're okay if everyone has some idea of what our salary is, but not the exact value, right? So back to the plausible deniability idea, right? So we're going to loosen our definition of privacy. And by the way, in crypto, they do this as well. They have different definitions of privacy, and depending on the one that you pick, you have a different algorithm, right? So weaker, weaker and less stringent requirements probably means that there is a more viable algorithm, right? So let's try seeing what happens. Now, this is the most common solution that people come up with. There's nothing wrong with it, by the way. I hope you know. I hope you know this by now, right? So if you did try this earnestly, or you came across this solution before, right, and you didn't hear it mentioned until now, right? It's not because this algorithm was wrong or anything, and it's not because those algorithms were better in any way. It was just worth discussing what the trade-offs were, right? So for example, there is this algorithm that we can think about as well, right? Where everyone just samples from a Gaussian, right? Centered at zero and with some standard deviation and then adds it to their sum, right? And at this point, you might think, hold on, Eldon. This is pretty much the algorithm that you gave us before, no? And you said it wasn't really that good and we tweaked it. True to some extent, right? But let's just see how well it performs, right? So here's an idea. How about we just compute these sums, okay, from this Gaussian, and we add them like these are different samples, by the way. So this sample is different from this sample and so on. They add it to their sum, and then we just broadcast the values as before, right? How do we compute the average? Well, then we would just say what we want to do is basically compute the sum, which is adding up everyone's message, right? Which happens to be 5 Gaussian samples plus your sum, which works out to be 125. Then to figure out what the average is, which is your output of your algorithm, just divide by 5, right? So I don't know if you know this, but a Gaussian distribution plus a Gaussian distribution is actually a Gaussian distribution. And I think if you do it carefully, you'll realize that it basically works out to be basically the average value plus a Gaussian. Yeah. Um, Interesting that this is actually kind of a neat trick. It satisfies something called differential privacy. There is an actual definition for this. I forgot if you use this distribution or if you use the Laplace distribution, but there is a distribution for this. Yeah, you can Google Laplace distribution if you want. It's quite interesting. You basically do one of these things and it gives you a very nice privacy guarantee. Not the uniformly random one, it gives you something else, but it does satisfy some notion of privacy. Yeah. So this could be one way of doing things as well. Like, I don't know, it depends on what our privacy requirement is. Design your algorithms differently. And you can imagine how now if there are n-1 colluders, they can't exactly figure out what your value is, because what they will see is your salary. Hypothetically, let's say your salary is 20. They will see your salary plus like some Gaussian. So they might not see 20 exactly. They might see like 27. They might see 21. They might see like 17, right? They could ask you, is your value close to 17? You could tell them maybe, maybe not. I don't know, right? They'll have some reasonable confidence, right? Because they can draw a confidence interval and they'll say like, oh, I'm reasonably confident, like it's within some range, right? But they won't be able to pinpoint your value directly, right? None of the n-1 colluders will be able to do that, right? So you can imagine how, let's say that we really want to beat n-1 colluders, maybe we should be satisfied with a solution that is approximately correct. This is something that we might have to sacrifice, right? We noise the solution a little bit and have a slightly less accurate solution for just a little bit more privacy. Maybe we really want a solution. We really want an exact answer. Then maybe we can't sacrifice. Then maybe we can't beat n-1 colluders and we have to sacrifice a little bit and go back to one of the previous solutions. Yeah. Okay. So what were the takeaways before I end the video? Right. I want to come back to this chart here, this table here. Okay, lot of scribbling. Right, and I want you to sort of take away the fact that sometimes, not always, but sometimes, right, it's designing and thinking about algorithms is more of a choice of like what trade-offs we are happy to make, right, rather than us just saying there is one God algorithm that solves all problems. Sometimes that will be the case where we have like one algorithm that is like best in like almost all regards, and we will almost always pick it. But this having this perspective, I think, is really helpful for learning algorithms. All right, so I think that sums up the recitation video. See you guys next week.